Our first speaker is Andrew Thomas. Andrew is a joint replacement surgeon at the Royal Orthopaedic Hospital in Birmingham. He specialises in the treatment of patients with rheumatoid arthritis who have compromised immune systems and are at high risk of deep infection. He's also got a research programme on operating theatre airflow and air quality jointly with the Department of Chemical Engineering, and has collaboration with microbiology with the Hospital Infection Research Laboratory. Andrew is going to talk to us this afternoon about fluid mechanics of ultra-clean operating theatres and microbiology contamination of surgical instrument trolleys. Andrew, it's all yours.
Okay, so this talk is on operating theatre air, and it's really centred on a happy accident which made me stray into instrument sterilisation. So there's a lot of talk in orthopaedics at the moment about the treatment of infected joint replacements, but as Louis Pasteur pointed out, it's a great deal better if you can prevent it from happening in the first place. So there's a great team of people that's been involved in this, a great team of engineers, and also the Hospital Infection Research Laboratory. And Tina Bradley's enthusiasm at the start of this project was absolutely invaluable to me. So the National Joint Registry is worth a look if you don't look at it. It documents our deep infection rates, and the current deep infection rate for joint replacement is probably around 1%. And the cost of this is absolutely horrific, both to the NHS, the cost in suffering to the patient, and the cost to society. And if anything, it's not getting better. It may even be getting worse, although that may be partly due to better diagnosis. So this is my operating theatre at the Royal Orthopaedic Hospital. It's an ultra-clean air system, and the surgeon and the assistant are connected to these body exhaust tubes. And there's a pretty high level of theatre discipline is being enforced here. And with this system, in the National Joint Registry, at 3 years post-surgery, my infection rate's about 0.36%, and that's in spite of the fact that the best part of a quarter of the patients have got rheumatoid arthritis. And the mechanisms of infection here are reasonably well worked out for lower limb joint replacement surgery, and there are some holes in the evidence here. So, for example, the microbiology of infected shoulder replacements is not quite so easily explained, but basically the ultra-clean air operating theatres are what you need to minimize the infection rate. And there's some newer evidence on this. This was a great study from Ghana, where they took a low-tech operating theatre doing clean soft tissue surgery. And they sucked the air from the operating theatre and stuck the plates in a freezer. And then they waited for the patients to develop wound infections. And about 8% of them got wound infections, and they were then able to cross-correlate the genomics of the wound infection with the air in the operating theatre. So a good method of looking at air quality in operating theatres is with settle plates. And so this is a study from Italy where they looked at 28 hospitals using settle plates during joint replacement surgery. And John Charnley, back in 1972, he got 0.2 colonies per 9 centimetre plate per hour. And here they were in Italy, 5 times worse, so that's not terribly good progress. So I decided to look in our operating theatre, and it was a straightforward audit. And so the surgeon and the assistant were wearing a body exhaust, And the scrub person, they didn't really like these body exhausts, this blooming thing Mr. Thomas tries to make us wear. It's too heavy, we get neck ache, I'm not doing that. So they wore what they liked, and we actually weren't too bad. Then what happened was that the hospital changed the personal protection system, and I used that as an excuse to upgrade the body exhaust system and force the nurses to wear it. And so we did this, and slightly to everyone's surprise, and it was Adam's lab that did this work, we were 8 times better. So we weren't totally sure that we believed this, but of course we published it anyway. And so what we found after 33 hours of surgery was that, if anything, most of the contamination was landing on the surgeon's side trolley at the opposite end to the surgeon. And it seemed that that was possibly due to instrument transfers, but the distribution of the colonies on the trolleys did not reach statistical significance. So I'd been interested in this for a long time, and this is a laser imaging study that I did with Cranfield, and it shows the circulation of air over the trolley and underneath the operating lamp. And the operating lamps have been known to be a problem for since the days of John Charnley. So I thought, well, this is really interesting stuff. We need to do more of this. So I went along to chemical engineering in Birmingham, and what they said to me was, Andrew, that's a load of pretty pictures, but what you really need is data. So we invested in this instrument, which is a 3D ultrasound-based anemometer, and it measures airflow in 3 directions, and it samples at 32 hertz. So you can do interesting stuff with this. So you can set it up at the corner of the clean zone and walk past it, and you can visualize the amazing disturbance in airflow at the corner of the clean zone when you do this. So we then use this to look at anesthetic screens. So this is right at the end of an operation, after the dressing's been put on. We wheeled this thing in and measured the airflow, and we checked it with some smoke. And what we found was that there was an absolutely miserable level of airflow just right over the patient. And all you had to do was to move the anesthetic screen back by 500 millimeters, and it profoundly alters the situation. So then we were also interested in thermal warming blankets, because we were told that these hot blankets would produce an upflow of air in the operating theatre that could be dangerous. So we invested in this unbelievably expensive camera, which we only rented for a week. And I wandered around the place taking some video. The first thing we noticed was that the temperature of the surgical team was pretty well as high as the warming blanket. And okay, you get rid of the warming blanket, but you can't get rid of the surgical team. And so we had some students, French students, very laboriously went around all of the different photographs, and there's 18 million temperature measurements. And the warming blanket was just marginally warmer than the staff, and there's absolutely no chance of the warming blanket having any effect on the airflow in the operating theatre. So then we decided we'd get a comprehensive view of the theatre. So we took Theatre 3 at the Orthopaedic Hospital, and we marked it up in 500 millimeter increments. And a couple of students measured it, and they produced this map of the velocity in the room. And we were kind of encouraged by this map because it correlated reasonably well with what we'd seen with the laser imaging experiments. So then the engineers got a bit warmed up and decided to produce a computational fluid dynamic model. And so the hospital very generously paid for a company to measure precisely the amount of air that was coming out of the system. And we measured the theatre very precisely, and we measured the tables, and we measured the light. And I took myself to this fancy photographic studio who produced a 3D model of myself. And the University of Birmingham was very generous with this massively powerful computer. And so we produced a computer model, and the engineers validated it against the anemometer data. And so this is the first output. And what you're looking at here is the arrows are the velocity of the air, and the background color is the age of the air. And when you run the system for just over a minute, what you can see is the stagnant area behind the anesthetic screen and the rather stagnant area around the scrub person and smaller stagnant areas behind the surgeon and the assistant. And then you can slice it the other way, and this showed a remarkable correlation with the velocity measurements that we made when we messed around with the anesthetic screen. And the data from the CFD model correlated reasonably well with the measurements. And then also you can look at the age of the air in the room, and this gives you a visual impression of the stagnant areas of air within the ultra-clean zone. So I decided it would be interesting to look at the particles which are expelled from the surgical clothing if you don't wear a body exhaust. So I went back to the photographic studio and had a model made of myself without a hood on. And we got the anemometer, and we measured the velocity of the air that is pumped out of the surgical gown. And then we went to the literature, and we looked at the Macintosh papers on the size of skin scales. And the skin scales, they're kind of awkward because they're flat. And so you have to translate the flat scale into an equivalent round object, which is a little difficult and slightly uncertain. But the properties of these things are known. So what the engineers then did was, this is me in a totally stagnant room, and this is expelling 1,000 skin scales of mixed sizes from my neck. And then what they did was they put the model of me into an ultra-clean zone, and of course it profoundly alters what happens. And we were pretty pleased with this because it correlated reasonably well with what we'd seen in the laser imaging experiments when we ejected smoke from the neck of this dummy. And when you remove the light from above the dummy, it profoundly alters the airflow. So then we put the whole thing together, and when you run it, what you can see is that the stuff that's coming out of the neck of the surgeon and the assistant is reasonably well dispersed, but the skin scale, any skin scales that come out of the neck of the scrub person who's standing under the light are going all over the place, and in particular they're ending up all over the two instrument trolleys. And that's the explanation for why, when we forced the scrub person to wear the body exhaust, it made such a difference. And all you have to do is to move the light out of the way, and you totally solve the problem. So then we got onto the instrument trolleys. And one of the things we'd noticed when we ran these models was that there seemed to be a stagnant area of air just over the instrument trolleys, kind of just really where you don't want it. And so we decided to work out if this was real. So we dressed up an instrument trolley and we dropped some smoke on it, and it looked as if it was real. And then we did some laser imaging, and that shows it in more detail and seems to confirm the observation. Now, this isn't really a new observation. So this is Willis Whitfield, the engineer from the US Scandia lab who produced the first clean room. And this is Whitfield's patent clean room from the early 1960s. And it's got a perforated metal floor in order to improve the pattern of the airflow. So I thought, well, maybe we should have a wire surgical instrument trolley. So down to my garden shed, and this was the very first prototype. And of course, when we tried it out in the clean zone, wonderful, totally different. And even when you put a wire instrument basket on it, it slows it down a little bit, but it still seems to have the same pattern. And also we measured that with the anemometer because we like data, we don't really like pretty pictures. So the second proof of concept prototype was made by Multimesh UK, and Jill Ford was really helpful. And so this is a fold-out autoclavable instrument basket that doubles as a tabletop. So here we are, and you've got to imagine that I'm the scrub person. And so this sterile arrangement has come from the TSSU, wrapped up in all this plastic. And so these sterile things here that look slightly like stainless steel condoms are being put onto the top of the instrument trolley. And then the basket goes on it. And then you take out the two remaining ones and put those on the on it there. And you open it up, and there is your instrument trolley. So that's roughly where we are at the moment. So I took it down to John Pendergast because I knew that he was interested in sterilizing things. And then we agreed that we ought to do some microbiology. So what we did was we took foot surgery because it's done in an ultra-clean theatre, but it's not done all wrapped up in the body exhaust and all super sterile. It's sterile, but it's not super sterile. And what we found was on the control trolleys, we were growing 0.2 colonies per plate per hour. And on the wire trolley, we were growing 0.1. This is not statistically significant. The Hospital Infection Research Laboratory has got a very severe statistician, and I've been banned from telling you this is significant. It's going to take a long time doing it this way. So what we are going to do is we've devised a system with a different version of the light that some poor person can stand underneath. And they've got to stand underneath this thing on a treadmill, and we've tested it to make sure that the airflow does what we expect it to do. And then some poor person who's looking for a job in orthopedics is forced to walk on a treadmill and disperses bacteria all over the place. And if he disperses a lot of bacteria, we won't give him the job anyway. Another thing, which is what I went to see John about, is that when you look at one of our joint replacements, there's an astonishing amount of this drape is used. And so what I did was, at the end of an operation, I took it away and measured it. They thought, Thomas has gone totally mad now. And so there was 37 square meters of drape. And when you multiply that by the number of joint replacements in the National Joint Registry, it's 7.5 square kilometers of plastic crap that gets thrown away every year. It's a total disgrace. And so what I think is that even if there isn't a massive microbiology advantage, and there may well not be, here's a method by which we could be saving the planet, even if we don't save our patients. So that's really where we are at the moment. I'd just like to talk a little bit about monitoring microbiological performance. So AstraZeneca UK apparently use about 1 million microbiology plates to check whether their pharmaceutical production line is adequately clean. And the NHS, for in-surgery, doesn't use a single one. And I just don't actually think that that's quite good enough. And in Italy, there was this great study recently where they just used, they actually used volumetric air samplers for the monitoring, which is a bit more hassle than using settle plates. But what they found was, and they ran this over a period of about 15 years, and steadily, they managed to improve things. Whether they really did anything, or whether it's just the effect of people looking at them, I wouldn't like to say. But, you know, I just don't think a patient would understand that we don't check whether we're doing our job properly. We've done air quality monitoring in my theatre with Adam's unit. But you have to have a real professional that come along and do this and run the Casella slit sampler. And actually doing it with settle plates, which you can stick right next to the wound and you can stick on the trolleys, seems to me to be the best way forwards. So that's our efforts to look at theatre air quality. And I'd like to thank the Royal Orthopaedic Hospital for funding hours of my time, the University of Birmingham for funding the summer students and the computing facilities. And I've been made for my sins the advisor on infection prevention to the British Orthopaedic Association, and we're going to run these settle plate audits as audit projects in orthopaedic departments. And Cherwell Laboratories have been very helpful in producing packs of settle plates that we can use for this purpose. So that's what we're up to, and thanks very much for listening.
Hello? Yeah. Thank you, Andrew. That was really interesting. Thank you. I used to work in the operating theatre, so it took me back. Any questions for Andrew? Could I ask one, do you still use the open trays? You still use the open tray for your for the scrub nurse to set up on?
Yeah, so our instruments come in a combination of different ways. So some of them come in the sealed box sterilization containers, and some of them come in wire trays. And it's basically mainly our own packs with like the basic instruments that come in the wire trays, and the stuff that comes from the companies like the reamers and stuff tend to come in closed containers.
Okay, thank you. Question?
Hi, sorry, Mark Wilkinson from Breebron. Just one question, did you do any monitoring of the lay-up area? The
lay-up area, so we, for the joint replacement surgery, our scrub people lay up in the clean zone. They wouldn't lay up open instruments in one area and then wheel them into the clean zone. That's a definite no-no. Whether this is really a good idea or not is a pretty interesting subject, because what we do is we have a pre-prep in the anaesthetic room, and we do that basically because John Charnley said you should do that. But there is quite a lot of evidence that the first prep of the patient does shed a huge number of bacteria into the air. Now, when you do the second prep in the clean zone, you also shed a lot more bacteria into the air while you're doing that than you do during the actual surgery. And we know that because one of the environmental microbiologists from the lab at the QE did some Casella samples at various stages of the operation. So whether it really is a good idea to do the second prep in the clean zone while the instruments are open, I think that's up for debate. And so I think, for example, one thing we should look at is we don't use ultraviolet in operating theatres now, but I've seen the system that they used to have at Brigham and Women's, where the whole theatre was flooded in UVC. And this was wonderful because it killed the bacteria, but also it forced the blooming anaesthetists to wear their hat and their mask properly, otherwise they got skin cancer. So, so as a method of enforcing theatre discipline, it works. And as a method of killing bacteria, it works. And, you know, maybe we should be looking at something like a directed UV beam, which is just over the instrument trolleys, maybe turned on while the second stage of the prep's being done. But, you know, a separate layup area, that's a no-no in joint replacement.
Okay, thanks, Mike.
Is there... The only other thing that occurred to me was, is there scope to redesign those lights so that they could actually be part of the filtration unit above? You look at the sort of the quality of LED light these days. If you've got a big square like this and it was flooded with light, would that give you sufficient light? Should you get rid of those floaty lights?
My patent agent is in the back of this room, and if I answer that question, he'll shoot me.
Excellent. So I'm pleased to hear that.